Assalamualaikum and good day everyone. Okay, now we go to the week 1 of the lecture for digital electronics. The course is CSEU 1223. Okay, the lectures hours. Okay, you can refer to the lecture schedule and the C schedule that we have agreed on, which is Monday 3 to 5 and also Tuesday 3 to 5. Lecture attendance will be taken. Make sure your attendance is more than 80%. Okay, the assessment, quiz, assignment, and presentation make up 20% of the marks. The test will make up of 30%, and final exam will contribute 50% to your overall marks. So this is the reference that we will be using. Make sure you have one of this book. Okay, so chapter 1, digital logic overview. So here we will discuss about the digital and analog quantities, binary digit, logic level, and digital waveform. Digital and analog quantities. Okay, so now we see first for a definition of analog and digital. For analog, it is a quantity that has a continuous set of value, which is a variable signal continuous in both time and amplitude. For example, for this temperature, okay, for this analog of the temperature, you can see the time here is day and this is the amplitude. You can see the temperature variation towards the time frame from 1 a.m. until 12 a.m. So this is the analog signal, means the real distribution of the data. The digital is a quantity that has a discrete set of value. Okay, so now we see from the same temperature data, we see this discrete value of the temperature in terms of digital. You can see we have the discrete value for this one, 1 a.m. this value, 2 a.m. this value, and so on. So you can see, right, this is the discrete set of value. Unlike for the analog, we have a continuous. You see, it's a continuous. In analog versus digital signal, for example, here in the analog, we use base 10 to represent our analog, the decimal. So I think in secondary school, we have studied this where we have like 2 to the base of 10. But due to the common use of this, we only use 2. Okay. But here, actually, there is a base number here. Okay. So for base 10 means the digit is from 0, 1, 2 until 9. Okay. Analog system is a combination of devices that manipulate values represented in analog. For example, you have analog watch and analog phone. Analog watch is the one that we use it with a okay. So this is represent the analog watch. Okay. So digital 2 is one of the example. Base 2 is one of the example of the digital signal. Okay. Here base 2 we refer it as a binary. So means it using 2 representation, either 0 or 1. Okay. Represented by 2 different levels. So digital system is a combination of devices that manipulate value represented in digital form. For example, your digital watch or your mobile digital phone. So here you can see is 0. You can see there is a changes of level in this grid. Okay. Here you have your 0, you have your 1, you have 0, 0, you have your 1, you have your 0, you have your 1, and so on. Okay, advantage of digital system. It is easy to design. Information storage is easy. Accuracy and precision are easy to maintain. Operation can be programmed, less affected by noise, and more digital circuitry can be fabricated and on IC chips. Okay, for example, the gates. Okay, we can fabricate a lot of gate inside the IC chip. IC is integrated circuit. Integrated circuit. So in the small area, for example, in this IC chip, in this wafer, you can have a lots of chips inside. Okay, easier to design. There are only two different voltages to be considered in the digital signal. It is either high or it's either low. So for example, in this, you see, there is only here region that we consider is high, binary 1. This is low, which consider as the binary 0. So VH min is the minimum voltage to be considered as high, and 5 is the maximum voltage to be considered as high for binary 1. Likewise, for low level, which is binary 0, 0 is the minimum voltage to be considered low, and 0.8 is considered as the maximum voltage for binary 0, while this region is the unacceptable voltage. Okay, information storage is easy because the information can be kept as long as necessary in digital memory and can be stored more compactly, such as last time we have cassette player and now we have CD player where we store the information of our digital data. Accuracy and precision easier to maintain. The digital signal does not deteriorate once it is stored. The analog information may be distorted by the effect of temperature, humidity, and etc. For the digital signal or digital data, it is easy to program and reprogram the operation of digital system. The operation in the analog system are complex and are difficult to program. For the digital system, it is less affected by noise. Why? Because the exact voltage not important in the digital system, because we already categorize, like for this one, we already put that anything falls in this value, it is binary 1. Anything falls within this value, it is binary 0. So it's using high-low comparison and 0, 1 bits to represent it. The next one is more digital circuits can be fabricated on chip. Analog components such as high-value capacitors, precision resistors, inductors, and transformer cannot be economically integrated. As you know, the transformer is actually bulky and so on. Okay, digital circuit easy fabricated using silicon technology, which is cheaper and easy to produce. Okay, normally for digital circuit, the integrated circuit, for example, okay, it can be as small is okay, the scale can be very small, and you can fabricate this like millions in a wafer. For example, you have a wafer, then you have actually million of diodes inside. Okay, very small. You may need a powerful microscope to see it, and actually a chip in a chip you can have maybe how many of these diode inside it. Okay, so it is very small. You can have transistors, you can have many things inside the integrated circuits. The limitation of the digital system is that the real world is analog, so it is not really able to represent it accurately as what is in the real world, because it is a digital. And remember that we take values to represent it in 1 or 0 form, for example. Processing digitized signals takes time and short product half-life. So here is the example of the conversion, okay, of the signal from the digital back to the sound wave, which is the analog. Okay, so you have your binary CD drive, then you have the digital data, then you go towards the digital to analog converter. We put this digital to analog converter. Here, the digital will be converted to analog. Okay, and analog reproduction of music audio signal, we go through a linear amplifier to amplify the signal. Okay, so here is in, for example, is decimal. Okay, convert digital sound CD to analog, process, amplify the analog information, then we convert the analog signal to sound. System using digital and analog method. Although a digital system has many advantages, real-world quantities are analog. Therefore, there is need to convert between analog and digital signal, as in the previous example. This is another example for microphone. For example, microphone is the analog to digital converter, ADC. So it's convert, and we go to the digital signal processing. We have memory, digital to analog converter. Then the speaker is the output of the digital to analog signal. Then we hear the sound. So the sound is the analog signal. Now, digital logic level and digital waveform. Binary digits. Digital electronic involve circuits and systems that are only two possible states, which is high represented by bit 1, low represented by bit 0. Each of the bit of the 1 and 0 is called bit in a binary digit system. The logic level, the voltage are used to represent 1 high and 0 low are called logic level. The voltage used to represent 1 or 0 is called logic level. So this is your logic level. So for bit 1, the logic level is 25 to be considered high. For bit 0 is 0.2, 0.8 volt to be considered low. And this is the undefined logic level, undefined, which is 0.8 to 2.22 volt. Digital waveform consists of voltage levels that are changing back and forth between high and low. So you see this is a digital waveform. This is the time from T0 to T1, and when it is rising up, we call it rising edge, and when the signal is falling back, we call it falling edge. Likewise, for this, from high is falling edge, and for high is rising edge. You can see here it is called positive going pulse because it is moving like this. So this one negative going pulse because we can see as time goes by it is going to the negative. In positive logic active high, the high is bit 1 and the low is bit 0. Whereas for the digital logic active low, the high is actually bit 0 and low is actually bit 1. So here this is 0, 1, 0, 1. But for this one is 1, 0, 1, 0. Oh, sorry. Sorry, my mistake. For this one is 0, 1, 0, 1. Okay. Digital waveform, two types of digital waveform, which is periodic or non-periodic. How to differentiate? The periodic signal, the signal keep repeating after period of time. You can see the same after the same time, the same period of time. Let's say 5 seconds. This one 5 seconds. The signal will repeat it again. The shape of it. So you have this as a one period. This is the second period, and this is the third period. And for the non-periodic, it doesn't have period, means you don't have a repeating signal. Okay, for example, like this, it's different, right?